Section 6.1, a first approach to connectedness. Well, if you're not convinced yet that topology is a good way to describe a shape and its properties, and here's some more evidence. Turns out that connectedness can be given a good definition just in terms of the neighborhoods of the open sets in a topology. And here it is. Let X be a topological space. We call X connected if there does not exist a pair of disjoint non-empty open sets whose union is X. And X is disconnected if X is not connected. So if there does exist some pair of disjoint non-empty open sets whose union is X. And in that case, that pair of disjoint non-empty open sets whose union is X is called a separation of X. Okay, so sort of simple case, if you have X being just a union of these two regions, say the subspace topology from R2, then these two pieces could be they're certainly disjoint, they're certainly non-empty, and in the subspace topology, they would both be open. Okay. And their union is the entire space X. So this would be a separation of your space, and that space would be disconnected. All right. So here's a problem for us to try. Let X be a set and assume that we have a point P in it. Prove that every subset of X that contains P is connected in the particular point topology on X and in the excluded point topology on X. All right. Well, okay, so let's begin with the particular point topology. Let X have the particular point topology at the point P in X. And, okay, we're supposed to prove something about every subset. So let's consider a subset A in X, and we can assume that it contains P. All right. Now, to show that this is connected, I am going to suppose I have a pair of, how am I going to do this? A pair of non-empty open sets whose union is X, and I'm going to prove then that they cannot be disjoint. Okay? Therefore, there's no separation of X, therefore X is connected. Okay, so suppose U and V are non-empty open sets in A with union equal to A. So that they're almost a separation, but we're going to show that they can't quite be, right? We're going to show that U and V cannot be disjoint. All right, that's our game plan. So, well, by definition, what does it mean that U and V are open in A, right? Open the subspace topology on A from X. It means that, okay, by definition of the subspace topology on A from X, there exist, well, non-empty open sets U prime and V prime in the big space X such that U prime intersect with A gives us U, and V prime intersect A gives us V. Okay, so in my picture here I have U and V whose union is my subset A, and then the fact that those are open in A means that we have U prime, which is this whole space in X, and this is supposed to be a V prime down there. Let me add that prime on. Okay, V prime in X, there's open in X, and such that V prime intersect A is V. All right, and then, well, these sets U prime and V prime, and they're open in X, right? And they're not empty. That means they must contain V by definition of the particular point topology. Okay. So they must both contain P. Okay. So here's where my picture breaks down, right? In fact, U prime and V prime would have to contain P. And since P is in A, U and V would also have to contain P. All right. Since P is in A, sets U and V also contain P. Right, because P is in U prime intersect A and it's in V prime intersect A, so it's in U and V. So they, meaning U and V, are not disjoint. And that finishes the proof. So there can be no separation of A, and therefore A is connected. Okay. Now let's try the same sort of thing for the excluded point topology on X at P. So now let X have the excluded point topology at this P in X, and consider a subset A of X containing P. All right. This time, instead of assuming I have non-empty subsets whose union is A, I'm going to assume I have non-empty subsets that are disjoint. I'm going to prove that the union cannot be A. Suppose that U and V are non-empty disjoint open sets in A, and we will show that U union V cannot equal A. All right. Well, we could start by showing that neither U nor V by itself can equal A. Right? Neither U nor V can equal A. Well, because these are disjoint, and if one of them is the entire set A, then the other one would have to be empty, okay? But they're also non-empty, so if either of them were A, that would contradict the fact that they're non-empty and disjoint. Okay, so because that would force the other set to be empty. Okay, well, these are open sets in A, so let's remind ourselves what that means. In fact, I think we can just copy that from up here. So, by definition of the subspace topology on A, there exist some non-empty, because they contain non-empty sets, open sets U prime and V prime in X, such that the intersection with A is the appropriate thing. Okay, so here's my picture this time. And now, what does it mean that U prime and V prime are open in X? Well, we're in the excluded point topology on X. So it means that either they're the entire set X or they don't contain P. Okay. Well, the first case can't happen. Note that U prime and V prime cannot equal the entire space X, since their intersections with A, as we just noted in the beginning, they're not A, right? They're proper subsets of A. Okay? So, I mean, if one of them equaled X, then its intersection with A would be all of A. Okay? In other words, U or V would be A. But we know that's not true. All right. So, we can rule out that case. Okay, so the only other way for U prime and V prime to be open are for them to not contain P. Okay. It follows that neither U prime nor V prime contain P. And if that's the case, well, remember U and V are subsets of U prime and V prime. And so they certainly don't contain P either. Right? The same is then true of U and V. And if neither of those contain P, then, well, there's no way that their union could be all of A, right? Because it would need to contain P, and it can't. So we can say that U union V is not equal to our set A. Right? And we extended U and V to open sets U prime and V prime in X, and we saw that those can't contain P, and therefore U and V don't either. But then there's no way that the union of U and V can be all of A. And that should do it.